Wow, sorry about that. All of a sudden, Zoom was giving me all kinds of trouble. I don't know what the problem was. So I rebooted the computer and it's back, but that was pretty annoying. But okay, so now we can get to it. So hold on, let me just get everything open for today, which I had open, but I had to reboot it. There you go. There's technology for you. All right, so what we have to do today is wrap up chapter 8. So let me get that open. There's just one more topic in here that we want to look at. And so we'll get to that in a second, but I also want to show you that on Zoom, not on Zoom, on Moodle, let's see, we have a problem set for this chapter that we will need to go over next week. Hold on one second. Where are we? Okay, so if you notice in Zoom, so I keep saying that, Moodle, down at the bottom here, there is a chapter 8 problem set that we're just about ready to go over. So when we're done today with chapter 8, you'll be ready for this problem set. This is it. And it's not terribly long. It's fairly time consuming because there's a lot of calculations involved. And it covers everything we've done in this chapter. It includes several word problems. So what I would like us to do is, since we're finishing chapter 8 today, let's go over this on Monday. And then we'll carry on with the new material. And at some point down the road, we'll start thinking about a second midterm. But right now, let's just keep going with where we are. So today we'll look at chapter 8, one last topic. And there's also a video that I want to show you that goes along with this last topic. Let me get that out there. Hold on one second. All right, so we'll get to that in a little while. Now, because this is not likely to take the entire class, there's also, we may as well start the next chapter, which is 11. Okay, so if you look at the syllabus, you'll see that we're skipping directly over chapters 9 and 10. We're going to 11. And so this is a very different topic altogether. And so I'll just open it up real fast. What's happening in chapter 11 is we're switching over to a completely different branch of mathematics called probability theory, which is actually quite interesting. And it's certainly very different than what we've done up to this point. And for this one, we do also have several very interesting videos to look at. So let's get back to chapter 8 real fast. And so one more topic and we'll be done with this. This one also involves formulas, but they're maybe not quite as complicated as what we've been doing. All right, those formulas for annuities were probably the most complicated formulas you'll see during the course. I guess that makes you happy. I don't know. But yes, these are fairly involved, but we did manage to get some practice last time, and we'll get plenty more practice when we do the problem set next Monday. All right, so by the time we're done, you'll be experts in calculating future values of sums, future values of annuities, et cetera, et cetera. Anyway, so within chapter 8, let's go back and find the topic that we will be looking at today. And what we're basically doing here is introducing the idea that there are actually two different equivalent ways that interest rates can actually be expressed. And so it's the kind of thing you might not have ever noticed when you go into a bank, but there's almost invariably two different interest rate quotes for any type of loan that you might be interested in, or any type of account that you've been thinking about saving your money in. There's almost invariably, in most banks, they have two rates quoted side by side, and we'd like to know what exactly is going on with these interest rates. So there's actually two different rates that we need to know about. And they are, let's see, where are we? Actually, I think I'm on the wrong slide here. Hold on. Oh, here we go. All right, I wrote this in by hand. All right. So there's two different ways of expressing interest rates. APR, which stands for annual percentage rate, which is also sometimes known as the nominal rate of interest. What it does is it represents how much simple interest you're being paid on your account or you're being charged for a loan. All right, so APR is used just to represent the simple interest. All right, so now the rate that charges or shows you both simple and compound interest is coming up next. Let me just give you a second to catch up here. So remember, there's two ways of expressing interest rates. The first one is APR, which simply means annual percentage rate, or sometimes it's called the nominal rate. And this one tells us how much simple interest we're getting only. It does not tell us anything about compound interest. So it's an important number, but it's not, it's somewhat incomplete because we also need to understand how much compound interest we're earning or saving, or paying rather. And so that rate, the one that really is more important, is called the effective annual rate, EAR, or sometimes it's simply called the effective rate. And how it's different is that it includes both simple and compound interest. So this is what you're actually going to earn on your savings, and it's also what you're going to pay when you borrow money. So you can see that obviously this is the more important of the two, but the EAR itself is derived directly from the APR. So you really do need both numbers. So the banks, when you walk in the door and you look at the interest rates that they are charging for different types of accounts, they have to either tell you both the APR and the EAR, or if they only show you one number, it has to be the EAR because it is, of course, the more meaningful of the two. So what we would like to know is how to calculate these. How are they related to each other? That's the key detail. And it turns out that the relationship between them is based on the compounding frequency. That's what really separates the two, the compounding frequency. And of course, you might remember that with simple interest, compounding is not relevant because simple interest is not based on compounding frequency. So we have a formula that ties them together. But first, I just wanted to show you a typical example. If you walk into a bank and say, listen, I'm thinking about putting my money in a 5-year CD, you might look up the wall and see that there's actually two numbers quoted, 102, 104. And you might say to yourself, why are there two numbers? That's because the first one, the lower one, is always the APR, and the second one, the higher number of the two, is the EAR. Now, usually they put these, EAR, APR, these are usually written in tiny, tiny little print underneath the numbers. So you may not even notice them. In fact, some banks don't even label them. They just have the two numbers. But you now know what this means. Okay, you know that the first number is the APR, the second number is the EAR. So if you're leaving your money in this account for 5 years, you're actually earning 1.04% per year because that includes the compound interest. Now, they don't necessarily tell you in the sign how frequently the interest is compounded, but in the US at least, it's almost invariably daily compounding. It's very rare that you find a bank that doesn't compound daily. So that part is sort of understood. So they don't really need to tell you what that is. What really matters to you as the saver is how much of a difference that makes to your the rate of return. So the daily compounding is what's responsible for you getting 1.04% rather than just 1.02%. And it doesn't look like a huge difference, but it really can pile up after a while, especially with large amounts of money, or else if it's a long time frame. Like if this is a 10-year CD, the difference would be even larger than you're seeing here. But anyway, what we want to know is how to calculate them. So here's the formula that we're going to use, and you can see it's very closely related to the future value of the sum that we've been using. So I put that formula down here in the bottom right-hand corner as a refresher of your memory. This is the formula that ties together EAR with APR. So that little r that we've been using in these formulas is actually the APR. And again, remember down here below, this is our future value of the sum formula. This r that we've been using is actually the APR. Once you take into account the compounding frequency, which is n, of course, then the result is your EAR. All right, so you can see this formula isn't really all that complicated. And it is, like I said before, directly related to this relationship between the principal that you're saving or investing and the future value. You notice that there's no T in this formula because this is an annual calculation. It doesn't really matter how many years you're leaving the money in your account. This relationship is the same or is determined by the N. That's what really drives the difference between the two, N, not T. All right, so we're going to go ahead now and do some examples of this just to see how much of a difference it makes between APR and EAR. And again, like I said, the difference isn't huge, but it's enough. You know, in other words, you wouldn't ever tell the bank that you don't need to worry about this, that you'll accept the APR. It's your money, okay? The EAR tells you that you've earned not only simple interest, but compound interest. So while the difference is not normally very large, it is important. So let's take a quick look at a numerical example. Suppose, let's say that the bank is offering APR 3%. And so in other words, you walk in the door and they say, our savings accounts offer 3%, but that's APR. That means that you'll earn 3% simple interest every year. But then if they further tell you that the compounding frequency is either A, annually, B, semi-annually, or C, quarterly, what does that do to the return you're actually getting on your account? All right, so that's the big question. In other words, what is the corresponding EAR in each of these three cases? All right, well, let's find out. Now, with one, the formula reduces very simply, and you might be just surprised to discover that when n equals 1, let's take a look at this case. When n equals 1, look what ended up happening. Look at that. The EAR is also 3%. So in this one special case with annual compounding, these two rates will be identical to each other. Because as you can see in the formula, when n is 1, all you actually have to do here is reduce this to 1.03 minus 1, and you can see that you wind up right back where you started with 3%. All right, but that won't last for long. What happens when we increase that compounding frequency up to 2? Well, let's see. All right, so this time we're going to change the n to 2 in our formula to figure out the EAR with semi-annual compounding. All right, so hopefully you have your calculators right there. So if you look at it carefully, you'll see that I've replaced the 1 with a 2. So ideally, what you would like to do is simplify this as much as possible. And if you notice directly below, I've written the fact that this is really just 1.015 squared minus 1. Okay, when you plug that into your calculator, you should get approximately 0.030225. And now for the first time, you can see there's a difference between APR and EAR. The EAR is slightly different. And so if you can see on the top, I've summarized them side by side. When the APR started out at 3%, the EAR with semi-annual compounding is 3.0225%. So that means when you walk in the bank and there's two numbers there, you know what they're talking about. Okay, 3% simple interest with the semi-annual compounding, we actually wind up with 3.0225% in our pockets. All right, so I'll give you a minute to catch up, and then we'll try the next case, which is quarterly. All right, let's try quarterly now. Oh, by the way, you know what I should have done? Let me see about the keystrokes. If you take out your calculator, I don't think this one is going to give you a lot of difficulty. Unlike some of the other ones, where the order in which you type in the numbers can get a little awkward. In this case, literally all you have to do is put 1.015 squared. Okay, remember there's a square button. And when you hit that square button, it automatically calculates the square. You don't need the equal sign here. Then you just put -1, but now you do need the equal sign. So put -1 equals, and that should give you your result. This is so much simpler than what we were doing before, isn't it? Yes, it is. Okay, because it's a relatively straightforward calculation. So 1.015 square -1 equals, and you're done. All right, so now let's switch over to quarterly. Okay, now this time you can see that n is 4. You're dividing this interest rate by 4, but then you're raising this to the 4th power. So let's see, maybe I'll put the keystrokes up here. You've got 1.0075. Now here, there is no 4th power button. So this is slightly different. You have to hit the exponential key. Okay, so 1.0075 raised to the 4th power. So x to the y at 4, and then you do need an equal here. And then you have your -1. Okay, equals. And that should give you this number down here. You can round it off a little bit. You don't really need all those decimals because the bank is rounding your interest to dollars and cents anyway. But here, that should be quite sufficient. So on the top, you can see that I've summarized this as 3% for APR and 3.0339% for EAR. And the one thing that you really need to notice here is that every time we increase N, the EAR gets bigger and bigger, whereas the APR never changes. All right, so that's an important note. I think I'll add that here somewhere. This is an important detail. Well, actually, before we do that, let's do one more example where we have daily compounding. So that wasn't originally in the slides. I added it afterwards. So let's see how that case would work. Okay, so with daily, of course, n is 365. Now, here's the awkward part here. 0.03 divided by 365 is a very small number. It has a lot of decimals. So in this case, I kept a lot of them. Maybe that was overkill. But yeah, it's better to keep too many digits than not enough. So, if you have a lot of digits, that's okay. So because here, and we're also raising this to a very large exponent. So because of that, the more digits of accuracy you have here, the better off you'll be. And you can see the result of all of that is 3.045%. And again, with the keystrokes, what you would have done is take your 1 plus, or sorry, 1.00. Now look at this thing. That's a big number. 1.000082192. The exponent is 365 equals -1 equals. And that would have been how you got to this 3.045%. All right, so this is a bit of a judgment call down here, how many decimals you keep. But this is fine because, like I said, this is going to ultimately be rounded to dollars and cents anyway. So this is accurate enough for our purposes. 3.00% for APR, 3.045% for EAR. Now, how much of a difference does it really make in your account? It depends. It depends on how much money you put in there and how long you leave the money there for. But it's it can pile up. Like I said, it's not that much in the beginning, but if you leave the money in your bank account, let's say for 20 years, you'll really start to notice it. Okay, it really starts to matter a great deal as we leave the money in there for progressively longer and longer periods of time. So that leads me to the conclusion that I was getting ready to build up to here. If you were to build up a little chart and summarize these results, what would you have? Let's say if I can insert a little table here. Let's see, how do I, okay. Let me see if I can plan this out. Okay. This is one of the annoying things about PowerPoint. When you ask for a table, it always gives you very peculiar choices. Like they've got green in there and yellow, but you notice how they start you out with green. Who would ever want a green table? I mean, what is that doing? I don't get it. But so here we'll have N, APR, and EAR. Okay, so when we had 1, 2, 4, and 365. Okay, and so 3% in each case. I'll leave it. Nah, it doesn't matter. I'll write it as 3.00. All right, so what I wanted you to see is how much the EAR changes. So the first one was exactly 3.00. The second one is 3.0225. The third one was 3.0339. And then finally, the last one was 3.045%. So what we want to take away from this, as you can probably guess, is that as we keep increasing N, the EAR keeps growing, whereas the APR never changes. And of course, you could fill in some of the other ones too if you wanted to, like 12, let's say, for monthly. But the bottom line here is that EAR keeps growing while APR never changes. Okay, so let's add this to our to the next slide. The chart shows that as N increases, two things are happening. First of all, APR never changes. And number two, EAR always increases. And in addition, when N equals 1, APR and EAR are equal. So these are basically the conclusions that we are drawing from all of this information. Now, if you have a credit card, when you get a credit card in the mail, they send you the card, but they also send you this document, this very thick, very densely written legal contract that between you and the bank, which spells out all the details about your card. And if you notice, they're required to tell you both the APR and the EAR. Now, with interest rates on credit cards, because they're so high, the difference between the APR and the EAR is likely to be very significant. Like I might say, for example, APR is 15%, but EAR is 19. So the difference gets really big as the interest rates go up. With 3, the difference is fairly small, but if this was 15%, you would have noticed a much bigger difference between APR and EAR. All right, so now I think it's time to get some practice. So what I'm going to do is grab that formula again so that we can do a little practice right now, make sure we really get this. Okay, hold on. So there's our formula. All right, so now let's try this. Just for the practice of it. I wouldn't call it fun, but let's call it practice. Suppose that the APR paid by a bank is 6%. What is the corresponding EAR when the compounding frequency is, okay, so we'll do annually, or annual, semi-annual, quarterly. Oh, okay, let's use the adjectives. And then let's say monthly. Okay, so in other words, what you're going to do is apply this formula. In fact, I'm going to copy this on here so you can see it. In all four cases. So you've got APR. Remember, that little r is your APR, and is the compounding frequency. What you're going to do is figure out what is the equivalent EAR in all four of those cases. All right, so the first one, even though you already know in advance what the answer is, why do you know that? Because remember earlier we said that when the n equals 1, APR equals EAR, but why don't we prove it formally? So just note that when we have annual compounding, n is 1, and in this case, APR is 6%, so you will put R equals 0.06 in the formula. So E equals 1 plus R over N to the N minus 1. And therefore, E will be 1 plus 0.06 over 1 to the first power minus 1, or 1.06 to the first power minus 1. And you can just see, you don't even need your calculator, that this will be 6%. All right, so what I'd like you to do is try that again, this time with n equals 2. Okay? And let's just see how much of a difference it really makes. All right, would you take a minute and see what you come up with? So I'm going to start making some changes here. All right, so what does this turn out to be? All right, we have somebody who has it. 6. Ooh, no, try again. It's 1.03 squared minus 1. $6.09, perfect. Okay, 609, which is the same thing as 6.09%. Excellent. All right. If you didn't get it, double check your results and see what happened. But mainly focus on here where we simplify 1.06 over 2 to the second is really just 1.03 squared minus 1. Okay, so that's what you should have. And then if you use the keystrokes correctly, you should end up with 0.0609, which means 6.09%. All right, so if you're ready, go ahead and try quarterly. And of course, that means n equals 4. Okay, so let's see. Let me get this one ready. Number 3, we're changing this to quarterly. Wait, 3, not 3, 4. Okay, so all of these become 4s. All right. Now this one will need to be rounded a little bit because it's a long, messy number, but let's see what we can get. Six 6.1363. Yes, that's it exactly. It's a long number, so let's round it a little. It's let's say we'll keep 06136. That's fine. Perfect. All right. And then finally, let's try what the last one was monthly. Okay, so that means n equals 12. So why don't you go ahead and try 12 and see what happens. This one also is a long, messy number. So in that case, let me just update this one. We're going to change this to monthly so that n is 12. All right, let's see what we've got. That's perfect. All right. 0.06, 16778, et cetera, et cetera. And it just keeps going on and on and on forever. So let's just round it to, let's say, 6.168, I guess. That's fine. 167. Yeah, you can round it to 6.7 as well. It's fine. I'll just leave it like this, I guess. So anyway, just as we suspected, each time increase the frequency, we ended up with a higher EAR. So I want to grab this chart again. I think it's a nice summary chart. This time, though, it'll be for 12, not 12, for 6%. And I just want you to see again the pattern that emerges. And so let's see what this one looks like. So now, sorry, when 6 is the APR, let's see what happens to the EAR. Now, the first one, of course, is automatically the same. But what about these other? Oh, that's right. And these are different too, aren't they? Okay, so let's get these going here. So the first one was 6.09. Exactly. The next one was 6.136%. And then the last one finally was 6.168%, let's say. So once again, you can see the pattern that's emerging here. In the beginning, these two are equal to each other. But after that, the EAR is greater than APR. And in addition, as we increase N, the spread between EAR and APR keeps getting bigger and bigger. So you're hoping when you go to this bank that you're getting a very high compounding frequency. So if you're a saver rather, you want a very high compounding frequency. But of course, this works both ways. If you're the lender, you do not want to see this because then you're paying more interest. But typically, the compounding frequency is the same whether you're borrowing or lending. That part really doesn't ever change. It's almost without fail daily. But for certain types of products, it's possible that the compounding frequency could be different. But for basic accounts like savings accounts or credit cards, most likely the compounding frequency is daily. All right. And so the next time you go into a bank, just pay close attention to those numbers on the wall. And whenever you see two of them side by side, you'll understand exactly what's going on. You'll know, oh, the one on the left, the small one is the APR, the one on the right, the larger one is the EAR, and I know how that was calculated. So that makes you feel pretty good because most people who walk in that door do not understand how this works, but you do. Okay, so that puts you a little bit ahead of the game compared to the other customers in the bank. All right, now I did mention that there's a video that goes with this, so let's take a look at it. Now that we've done all this, the video will make perfect sense. So let's see there. By the way, remember before I mentioned that the APR is sometimes called a nominal rate. The EAR is called the effective rate. The video is going to use the word nominal to describe APR. So don't be confused. This is fairly standard practice. APR is often called nominal. EAR is often called effective. So that's how they're going to describe it in the video. But just be aware that nominal means APR and effective is EAR. All right, let's take a look at this thing. All right, let me throw that up in the chat room. And then we'll check it out.
Welcome to Lemore TV, the place to be.
All right, are we done? Yes. Well, I thought she did a pretty good job of explaining it. But now the one thing that I did notice that she mentioned was that the when you hear an interest rate quote, it's typically the APR, and that might be true for some cases. Like if you go to the auto dealer and say, "Listen, I need to borrow money to buy a car," and they say, "Don't worry, we only charge 6% here." Most likely, they mean the APR, and then they'll tell you what the EAR is in the contract that they offer you to sign to borrow the money for the car. But and the same thing with credit cards. They might say, "Oh, look at our card is 12.99%," but what they're typically telling you then is the APR, and then but when you get the card, they have to tell you in the contract what the actual EAR is. So it's not the case that they can hide it from you, but they don't often mention it. Like when they're trying to get you to take their card or get, if the dealer wants you to borrow money from them, the number they quote you usually is the APR. But with the banks, they do have to show you either both numbers or the EAR because they know that that's the one that's really relevant. So, but for other cases, like she mentioned, like for car loans or mortgages, maybe the number they're quoting you is almost certainly an APR. And then if you want to, you can figure out what the effective rate actually is from that, or you can just ask them because they do have to tell you. It's just that they tend to promote the APR because it sounds lower. And that way, psychologically, it sounds like you're saving money when maybe you're not. But now in this class, we will never be fooled, will we? Because we understand the difference between the two and how one is related to the other. She also had that interesting example with the credit card. When the interest rate starts out at 20%, if your APR is 20%, the compounding will have an enormous impact on how much interest you're actually paying. Whereas if you have a very low APR, like in a savings account, the compounding will not have that big of an impact on how much you're earning because the rate is already low to start with. So the larger the rate of interest you have, the larger the APR, the more of a difference there will be between APR and EAR. So you have to keep that in mind when you decide to borrow money, especially. All right, so we're done with 8. Like I said before, we're now ready, not today, of course, to work on this chapter 8 problem set, which pretty much covers everything we've done. So now this chapter was kind of a standalone chapter. We're not going to discuss interest rates any further. Instead, we're going into a completely different branch of mathematics, which is probability, and that will be followed up by our first introductory look at statistics. Now, everybody has heard of the word statistics before. It is something that is used very widely in many different areas. You name it, most likely statistics are involved somehow. So it's important for everyone to have at least a basic comfort level with statistics because you're going to be surrounded by them no matter what you end up doing for your profession. And especially given that at some point, like I've said before, you're likely to have money to save and invest, and you'll have to understand how to calculate, for example, the average return to an investment or how much risk is involved. So the area we're getting into is more focused on understanding risk and uncertainty than anything else. It's a very interesting area of study, though. Very interesting. It can be applied to a lot of different areas. And the math itself isn't really that complicated, but the concepts that we have to learn might be a little challenging. Okay, so the focus is more on understanding the concepts than grinding out a lot of numbers. So anyway, just to get the ball rolling, I have another video here which will serve as our introduction to probability theory. And so now some of these videos I have found here are actually kind of fun, if you can believe it. So well, as we go along, I'll introduce these various videos, and then we can start looking at probability theory, which again is chapter 11. And along the way, we're going to learn some very interesting concepts, some of which are on your calculator, some of which are not. So we'll have to work with that as we go along. So anyway, let me show you this next video, which is called Basic Probability. And so this will give us a feel for what we're going to do in chapter 11. Okay, so hold on, here it is. Oh, no, that's not it. Okay, let's check it out. All right, are we all done? Yeah, that was good. I thought that was a lot of fun, and it helps on reinforce what we're going to be doing in this chapter. Just the basic foundations of probability theory, and you can see that it all comes down to something random happening, like a coin flip or the roll of a die. And so he made a lot of very interesting points. He showed you how to calculate different probabilities based on those experiments. And also, he reinforced the idea that when you have just a few trials, then the probabilities that you actually get or the outcomes you get are maybe very different than what you expect. But if you keep repeating these trials over and over and over again, you should eventually get results that make sense. Like when you roll the die and there were a lot more twos than fives, well, that's to be expected when you have very few rolls. But as the more and more rolls take place, then of course eventually it gets to the point where you have almost an exactly even number of ones, twos, threes, fours, and fives. So yeah, I thought, I thought it was very helpful, and it was a lot of fun too. I mean, it's hard to make math fun, as you can probably guess. The videos make it. You see the potential here to make it more interesting because of the graphics and the music and all and the sound effects, but it was extremely well explained. And so I thought this was a very good way to start this chapter 11. Now, what we're going to actually do is take a little bit of a detour before we start our discussion about probability theory. We're going to sort of take a side detour into an area which is called counting techniques, which sort of lays the groundwork for everything that follows. It's not really part of probability theory. Counting techniques are part of a separate branch of mathematics, which is called combinatorics, which has a very big role to play in probability theory. So before we even start to address probability, we're going to be looking at these different counting techniques. And I really think you'll find this to be very interesting. And when we're done with that, then we can move on and discuss actual probability theory. So we're going to start out with a very interesting result. And that result is called the fundamental counting principle. Now, you're probably saying to yourselves, I know how to count. What is this all about? But we're not really interested in just counting objects. What we're trying to do is count ways in which objects can be chosen or arranged or whatever the case may be. So if you see here, the magic word in the sentence is arranged. So what we have to do now is understand, what do we mean by the word arranged in this context. So basically, let's take a look at this example that's coming up. Suppose that you find yourself being spectacularly successful and you have an enormous house with a 3-car garage. And so let's show that with an illustration. 3, yes. So it's not a very good drawing, but you've got 3 garages side by side, which we will label garage 1. So you've got 3 cars, and so you're really doing great. You've got an Infiniti, you've got a Lexus, you've got a Mercedes. Here's the interesting question, though. Obviously, you have 1 garage for each car. The question is, how many different ways can you park these cars? Each way that you can park the cars is known as an arrangement. All right. Yes. Oh, yeah. Go ahead. Oh, I just realized. I'm sorry. I forgot to turn the thing on. Thank you for pointing that out to me. This is not the first time this has happened. Yeah, you're right. You know why? Because I had it turned off for the video. And so I'm sorry about that. Yes, let me just show you two again what we were actually doing. Um, yeah, yeah, the only reason I turn it off when the videos are showing is because I want to avoid any potential copyright problems. I had been informed in the past that by including the videos in these recordings, at least potentially, that could lead to problems. So my strategy now is just turn the recording off when we're watching them. No, that wasn't, no, that was my problem on this side. Yeah, I just forgot to turn it back on. All right. So I'm glad that you started to catch me here. All right. So let's go back and revisit what I was saying, that we're starting out with this branch of mathematics called combinatorics, which represents counting techniques, which will be used to create form the foundation for the probability theory that will follow. And so the fundamental counting principle represents or is a formula that we'll use to determine the number of ways in which a collection of objects can be arranged. Okay, the magic word there, like I said, is arranged. So we have to determine what exactly do we mean by an arrangement. Okay, so I start out with the example of of a house with three garages. Okay, you've got this enormous mansion, imagine, where you've got a three-car garage, and the garages are just simply numbered 1, 2, and 3. And you also own three really nice cars, which are the Infiniti, the Lexus, and the Mercedes. And so the challenging part here is to think of how many different ways can we park the cars in these three garages? Good question. So in the next slide, I've actually written them all out so you can see how many there are. I'm using I to represent Infiniti, L for Lexus, and M for Mercedes. All right, so I'll show them to you. Now, of course, the strategy we're about to use is sometimes called the brute force approach, because you're basically just writing out all the different ways of parking the cars, and that will work, but it's very time consuming. What we would ideally like to do is come up with a formula that will make this a lot simpler. Okay, so the first thing to do is just list them all. All right, and when we do that, you can see that it turns out there are 6 different ways that I can park the cars. I've got my Infiniti, followed by the Lexus and the Mercedes. And then over here, I've got Infiniti, Mercedes, and Lexus. And then we work our way down the list, and you can see that altogether, there are 6 different ways of parking the cars. Okay, so what you say? Well, each of these, all right, well, I'll give you a minute to catch up. But if you notice, there's 6 different ways we can do this. If you look through them very carefully, you'll see we did not miss any of the possibilities here. All of them are accounted for. Okay, so what we have here is a very simple example of what we will call arrangements. Okay, in other words, each of these choices or methods for parking the cars is referred to as an arrangement in mathematics, that is. It's, I mean, you hear that word used in other contexts. For example, sometimes you hear, like with flowers, let's say you bought some nice flowers and you had them put into a vase. It's often referred to as an arrangement, but that's a very imprecise terminology in that case. Here it means something very, very specific. It means the number of ways in which we can order these 3 cars. So these are known as arrangements. Now, the big question is, how could you figure out how many arrangements there are with a formula rather than having to write them all out? Okay, that's the fun part. And this is the part that I don't think, unfortunately, this may not be on your calculators, what we're about to do. But that's okay, because you can do it, figure it out yourself. So let's see what we're talking about here. Oh, here's another example. This might be even a better example. Suppose you have enough room on your wall to hang 3 posters from left to right. Each choice that you have for hanging these posters is also known as an arrangement. Okay, you're just taking the 3 posters and rearranging them from left to right, and you'll end up with, as we saw earlier with the cars, 6 different ways of hanging your posters. And each of those methods or ways of hanging them is called an arrangement. So how can we count them? or calculate the number of arrangements without having to go through the trouble of listing them all? Well, we have a formula. Well, first, let's think about the logic behind this. Let's go back to the garage example. When we start out with the garage, is what the way to think about this is that with the first garage, there's 3 different choices that we have for parking a car in the first garage. Okay, so in other words, let's say the cars are sitting out here waiting to be parked, and you say to yourself, how many ways can I choose a car to put in the first garage? The answer is 3. All right, all 3 cars are sitting there waiting to be parked, and you can pick any one of them for that first garage. But this is the interesting part. Once you've chosen a car for that first garage, how many choices do you have for the second garage? Well, now there's only 2 left. No matter which one you put in the first garage, there's only 2 more left for the second garage. So you have 2 choices for the second garage. And once the first 2 have been chosen, there's only 1 way to choose the car for the third garage because there's only 1 that's still left to be parked. So the way to think about this is that, yes, we can pick any of the 3 cars to put in the first garage. Once that's been chosen, there's only 2 left for the second garage. And then once that's been chosen, there's 1 way to park the third car. So therefore, the number of ways of doing this, since there are 3 ways of choosing the car for the first garage, 2 for the second, and 1 for the third, therefore there must be 3 times 2 times 1, or 6 choices for parking the cars. All right, so let's think about that for a minute. Does that make sense? This first number tells me how many ways I can choose to park for the first garage. This is how many ways I can choose a car for the second garage. And this is the number of ways I can choose a car to pick for the third garage. 3 times 2 times 1. And you see that we did in fact wind up with 6 choices. So this is how it would have been done. 3 for the first garage, 2 for the second, 1 for the third. The product of those 3 numbers is 6. All right. So now that we have this down, let's think about this for a minute. What if we had a 4th garage and 4 cars? How many different ways could we have parked 4 cars? So imagine ourselves going out now, buying ourselves a Rolls Royce. Okay, and we get a bigger house too, by the way. We go out and buy a bigger mansion. We've got 4 garages, and we now have 4 expensive cars to park. So based on what we just saw a minute ago, how many different ways can we park these cars? Well, you know what? Let's use the same type of reasoning. For the first garage, there's 4 ways we can choose the car to park. Once that choice has been made, there's only 3 remaining cars for the second garage. Once that's been decided, then we have 2 cars left for the third garage. And then finally, we have 1 car available for the 4th garage. And so the number of choices is now 4 times 3 times 2 times 1, which is 24. So you can see the number of choices is growing very, very quickly. So hopefully this logic makes sense to everyone. And also, again, all 24 choices are known as arrangements. In mathematics, they're called arrangements. Or if you want to think about it this way, imagine you've got room on your wall for 4 posters. The number of ways you can arrange those 4 posters is also 24, based on the same logic. All right, now we're going to now formally introduce a mathematical operator that will basically do the same thing for us, and this is called factorial. right? So the factorial operator is written as n with an exclamation point. I don't know where that came from, but this is the standard terminology or notation. N with an exclamation point after it is called n factorial. And this n factorial will be used by us to calculate the number of arrangements very quickly and easily, because when you see how it's defined, you'll see that it looks just like what we were just doing with the garages. So how does this thing work? By the way, if you do have a different calculator than the iPhone or one of the bigger Texas Instruments calculators, it probably has this key built into it somewhere. For the iPhone, we'll have to do it ourselves. So how does this work? Well, first of all, it's only defined for the whole numbers, meaning 0, 1, 2, 3, etc. And this is how it works. The first two are just equal to 1. Both 0 factorial and 1 factorial are just 1. But then it suddenly gets very interesting. How interesting does it get? Well, 2 factorial is 2 times 1, or 2. 3 factorial is 3 times 2 times 1, which is 6. Well, I think you can see where this is going. 4 factorial, as you can probably imagine, is 4 times 3 times 2 times 1, as we'll see in the next slide. Okay, so let me show that to you. Oh yeah, look at that. And then 5 factorial, 5 times 4 times 3 times 2 times 1, or 120. 6 factorial, 6 times 5 times 4 times 3 times 2 times 1, 720. So you can see the pattern that's emerging here. And so if you wanted to know how to arrange any number of objects, all you have to do is use n factorial. For example, when we had 3 garages, the number of ways of parking the cars was 6, and it's no coincidence that 3 factorial equals 6. Okay, so in other words, we figured out how to park the cars by multiplying 3 by 2 by 1, and we ended up with 6, which is just happens to be the definition of 3 factorial. When we had 4 garages, we didn't actually write them all out because it would have taken all day. But it turns out that with 4 cars and a 4-car garage, we could have chosen 24 different ways to park them. Again, based on the same reasoning, 4 times 3 times 2 times 1. And then if we had a 5-car garage, the number of possibilities would have gone up to 120. And then if we had a 6-car garage, this would have gone up to 720. So it starts to grow very quickly, doesn't it? Now, you might wonder, what are we going to do with this information? Well, don't you worry. We will put this to good use very soon in our study of not only probability theory, but statistics as well. So these basic concepts that we're learning right now, which are, like I said before, part of the branch of mathematics called combinatorics, are going to be helpful in helping us count for different types of situations. And they're just interesting for their own sake, I think. Anyway, so I don't want to get too far into this topic. Remember, next time, what we want to do is get that Chapter 8 problem set done. And this probably won't take up the whole class. It'll take up a lot of it, but maybe not all of it. So next Monday, we want to work on this set of practice problems for Chapter 8. And if there's any time left, we can come back and revisit this topic. and dive further into this area of combinatorics. And when that's done, we will get back into probability theory proper. Okay. All right. So I guess if there's no last minute questions, I guess we can stop right here. And I hope you all have a very nice weekend.
Bye. Thank you, sir.
All right. See you later. Okay, you too. Thank you.
Professor,
Yes, go ahead.
I just got back. I emailed you about a family emergency that happened that I had to leave the country for.
Oh, okay. When I forgot what the details were, could you remind me?
I went to Guyana and just came back.
Oh, you just came back.
But
Okay.
I
So,
Yeah, but I didn't have access to Wi-Fi, so I couldn't do the midterm.
oh, okay. Well, if you're out of the country, all right. You know what? I'll tell you what. Just send it to me during the weekend then.
Okay, thank you.
It's all right. I mean, obviously, you have a valid reason for not being able to do it. So yeah, go ahead. Just have it ready by Sunday night, and it should be fine. I haven't actually I have not corrected them all yet, anyway. So you can just send it in. It'll probably arrive right while I'm working on the others anyway. So that'll be fine.
Okay, thank you.
Okay. All right. See you next time. All right. Bye.